Welcome to the 10th annual workshop on Charm++ and applications. We have been doing this now for 10 years, like this says, and I think it's great that we can actually fill a two-day program with the work, our work. But this year we also have quite a bit of presentations from others, which is excellent as well. I'm going to start with an introductory talk with the highlights, and then we'll begin with the rest of the talk. So actually, we've had a really great year, and I'll give you a few highlights from the year that just passed, but also that we have several challenges coming up. Not the least of which is funding challenges, but also other kinds of challenges, and I'll try to outline those. I'm going to then give you specific highlights from the work during the last year, many of which you will actually hear in the rest of the workshop as well. So the first thing is, and I think the group here does not need any additional introduction to this, but I'm going to do it anyways, just in case. As you know, this webcast will be this workshop is webcast, and all our workshops for the past 10 years have been archived, and maybe at some point the very old one should be removed, but they're all there, I think. So just for the sake of that as well, I will for the completeness, I will introduce the basic model that we work on. So let's begin with that. So the basic idea of our programming model is to let the programmer or the compiler decompose the computation into work units or data units, and those are logical units. They're still making grain-sized decisions. Those are not automated, although they could be automated in part by the compiler of future. Right now the basic Charm model is the grain size decision is up to the programmer, and then which processor holds which work unit or data unit, which chunk, is up to the runtime system. This two-level hierarchy, hierarchy is part of the overall design. I wasn't talking about it here, but basically I think that this two-level hierarchy is enough to deal with multi-level hierarchy of the machine for various reasons, and we won't get into those reasons here. But you got to have that basic tiling, blocking, or chunking, or whatever you want to call it, to enable that such a thing. It also enables this idea, we'll call it over decomposition, and basically depicted here as, you take your application, you take the logical piece of work that you have, break it down into pieces. Each piece is not a scalar, not like every integer an object type of a philosophy, but a chunk. And then you do the same thing for another logical chunk. So you might have solids or fluids or whatever else you have. Each one of them gets separately chunked into their logical units, and then these chunks get mapped to the processors by the runtime. This is the basic idea in Charm++, as well as in adaptive MPI, which are both works from here. But as you can see, that these kinds of ideas are appearing in HPX, in projects out of Sandia, for example, Excalibur and XGC, and several others, and the task parallel stuff that you will hear about later today from Argonne as well has some resonance with these kinds of ideas. So the fashionable word these days is execution model, and there is some debate about what exactly it means, but Charm++ and adaptive MPI both share particular way in which programs get executed, and we'll call this the Charm++ execution model. It is characterized by macro data flow. You can think of it as connected with actors, although actors is a much more narrower and something oriented in a slightly different way, more semantic construct. So we have a whole bunch of differences with the pure actors as well, but the message-driven execution is a common feature with actors. We have migratable work and data units, and we have global namespace for these. And this global namespace is supported by some runtime that's flexible. That's kind of the basic characteristics of our execution model. This kind of conglomeration of ideas showing some good resonance in the overall field of HPC. And I think one way or the other, this will be part of the overall, the gene pool of the exascale landscape, exascale ecosystem. Maybe just maybe we hope it will, CHAMP++ will participate directly, and maybe these ideas, we and others will participate in combining them with other programming models as well. But I think these basic ideas over decomposition are very important. Over decomposition actually enables adaptive runtime systems. Basically, the runtime system can introspect. It is in charge of placing these entities on processors, scheduling them, and mediating communication between them. So it can introspect at will all that is happening at runtime, and it can optimize the communication, etc. Basically, pictorially, I showed this picture often in one form or the other. Over decomposition and message-driven execution enables scalable tools, because for a variety of reasons, for example, the message-driven execution that comes from that is actually easy enough to incorporate monitoring infrastructure without needing something like an MRNet on the side. So automatic overlap of communication and computation, ability to peek ahead and prefetch data and computation, all of those come, and compositionality most of all follow from simply that idea. But that idea of over decomposition also leads to migratability. We add migratability, you can move objects around the processors, and that leads in particular to fault tolerance. Migratability combined with introspection gives us dynamic load balancing, and we have research going on load balancing in various forms now, topology aware, scalable, meta balancing, just figuring out what kind of strategy do you actually need, and there will be a talk about that by Harshita later. Temperature and power aware load balancing, that can also that also follows from this introspection and adaptive runtime system. And then building on that is more higher level control points, which you can actually reconfigure the application itself in response to the runtime conditions, and higher level abstractions for programming. So this is kind of the overall computer science agenda of PPL, of our group, and then there is the application agenda. We work with several applications, and we'll probably hear about many of them in the rest of the workshop. So going to the highlights of this year, Blue Waters was probably the biggest one that we had the most people working on in the group on a single project, and so we're very thankful to the NCSA and NSF for the support that we got. But I think we also enriched the project in many ways. Of course, as you know, this year the big news was transitioning from the IBM design to the Cray design. I often say IBM machine was a very good machine. It was almost a dream machine, but in too real sense, it was a dream machine. It was not to be. So it was not real, and so yes, and Cray is a great machine as well. And so we made that transition very quickly and very in a very agile manner, I think. Kudos to the NCSA staff and Cray for that. And we have the machine, not here, NCSA, for those of you from outside, the NCSA is right next door through this window. The machine is a mile or two away from here. Tomorrow there will be a tour of the machine room. The early science system is in place there. I'm not sure I'm supposed to say how many cores and nodes, and the full machine will be deployed over the next few months. So it's going on schedule. Our role, our group's role in that, we had multiple roles there. One of those was simply to provide CHAMP++ and this virtualization idea on the new machine, and within that we have worked on load balancing, fault tolerance, and so on. There are PRACs, the so-called applications. There are maybe 30+ applications that have been selected by NSF to run on this machine. Several of those PRACs actually involve CHAMP++, NAMD, Contagion, Changa, Cello, at least in part, and several others are part of the, these three are the ones that we are directly involved in. These are collaboratively developed by PPL. Cello is one from San Diego. James Brodner is here, Mike Norman's project. And then there are several others that are considering CHAMP++ or AMPI to improve their performance. We also participated in network modeling quite a bit, especially when early days, you know, this was 5 years of a project before the machine was to be there, and so we had to model the network of the machine and how it will perform and how the whole machine will perform, and the whole BigSim project was very useful for that, and we refined the BigSim project in that, and we have several results to show for the PERCS network based on the simulations that we did. Turns out that those same simulation studies are useful for the new topologies as well, the new machine as well as, say, for example, the Livermore machine or any other machines. But the point is, oh, the machine is here, we really don't need any simulation anymore, is the prevailing viewpoint. However, I think sooner or later we'll see that the time you need for doing the experiments on these machines is not easy to come by, and so having a simulation thing as a backup, even when the machine is there for studying various mappings and so on, will still prove to be useful. So topology aware mapping as a specific area is something that we are working on as well, especially for the 3D torus. It's a very important thing. Of course, that also requires more contiguous mapping, awareness of the coordinates of the nodes and their placement in the topology, and all that we are working on. So we're looking forward to using the full machine and getting great results on it. So going through, and again, I'm going to be going through several highlights of the last year, and so maybe a little bit disparate and disjoint. One of the highlights is we got the best paper award for something that's unusual. People don't realize this, but the CHAM++ is useful for programming on single shared memory node as well. And of course, then that carries over into the fact that we have multi-core nodes these days. And so, so the reason CHAM++ is useful in this context is because locality is still important on a single shared memory node. The view that you can access any data from anywhere, which is kind of a traditional OpenMP view, even OpenMP is kind of changing slowly, is not valid because the locality is pretty critical even on shared memory nodes for NUMA reasons, but also for other simple cache-based reasons and so on. And so it turns out that the blocking capability and the localization that CHAM++ provides, as well as the object abstraction it provides, is pretty useful on shared memory node. Pritish was able to demonstrate that for a couple applications, specifically for KD trees, showed several optimizations, and also how the programming abstraction is both productive and high performant. So we were able to show results that beat a TBB-based state-of-art KDD tree construction code, for example. The next highlight I would talk about NAMD. There is this year there is no NAMD performance talk that we have directly, so I'm going to spend a few more minutes on telling you about the NAMD, about what we did with NAMD last year. NAMD is, of course, our flagship application. It was co-developed with CHAM++. In other words, CHAM++ and NAMD are kind of simultaneously moving forward, and it was also co-designed with CHAM++. The software architecture was done by us and Jim Phillips here and Bob Skeel. And servers, and it actually serves as an exemplar. What is its relevance today? Its relevance today, first of all, is that the parallel architecture that we chose in how many years ago? That was 15 years ago. Continues to work today. Okay, that's actually credible. It was a from scratch design, but it continues to work when the machines that we used there were kind of before people were talking about Beowulf. We had a 16-node HP cluster. That's what we were using at that time. From that to these 200,000 core machines of today, the same parallel architecture has withstood the test of time. But the more importantly, as we go further into multi-petascale and exascale times, it is clear that we are going to deal with strong scaling. We're going to deal with strong scaling because the memory per core is dropping, but even more from the point of view of the applications, the n-cube scaling, the difference between the memory requirements and the time requirements. As you make the resolution smaller, you actually have to take tinier time steps, you know, if you're doing explicit time steps, for example, or more iterations. And so as a result, your time typically grows as n to the power 4 and space as n to the power 3. For that reason, and for a variety of reasons, you're going to have to deal with strong scaling. The problems that we want to solve don't necessarily just become bigger because you have a bigger machine. In some domains like molecular dynamics, our biology is fixed. You have whatever proteins, DNA systems that we want to study, and those are the ones we want to study for a longer duration. The resolution is as small as it's ever going to get. And so this trunk scaling is kind of an important component of the future. And what does that mean? That means your time steps are going to be smaller. And this is one thing that NAMD demonstrates. It's an exemplar of this class. And you will see, basically you are going to need billions of time steps, and each time step therefore has to be completed in milliseconds if you can, and if you can maybe even go faster than millisecond. So the parallel structure, this is a diagram that we have been using all along. I'll use a slightly different diagram today, but you have the atoms decomposed into cubes, and then pairs of atoms in nearby cubes interact for non-bonded interactions, for bonded interactions, and also the third component, which is computationally very small, maybe 5% or so, which is the particle mesh AWOLD, which involves a 3D FFT. We have been using this picture for a while, but in fact for the last 5 years or so, we have been more like doing this. Instead of the plane decomposition for the FFT in the particle mesh AWOLD, we actually use pencil decomposition as shown in the right picture. And so that component, even though it is 5–10% of the computation, in fact turns out to become important as we do strong scaling, because as we do strong scaling, critical paths become more important. You can see this in this picture. You cannot actually see the details of the picture, but this is a simulation of a benchmark called DHFR, only 23 or 24,000 atoms running on 1,000 cores of the Cray Titan. And this is a time step, and some selected sets of processors just to see what's going on. The blue part here is the electrostatic non-bonded computation. The green part is that supposedly tiny PME computation. We have selected the processors that actually participate in that, so it shows up more than that. But you can see the critical path starts to dominate towards the right. Important point here: this time step is about 1.5 milliseconds. This is running on 1K cores. And so with several optimizations on this year we were able to get this down to here, number of cores on the x-axis, milliseconds per step. And when we were running on the MPI version of CHAMP++, that's the green curve that you can barely see in the back, going to 1 millisecond at 2K processors. And from that, when we went to UGenie, which is the native layer for Cray, we pushed the performance. We improved the performance a bit, and then after we applied several optimizations, that some of which you'll probably hear about there in a paper that's coming up, and we were able to get it down to maybe 600 microseconds per time step. And we are hoping to get further than that, but it's going to be tough. It's going to require breaking that critical path down through those green links of particle mesh AWOLD. If you look at 1 million atom going through the higher scale, running up to 8K processors, similarly the MPI version, the UGenie version in green here, different colors, sorry about that, and then the red color shows the current UGenie based CHAMP++ on Titan going to about 2.5 milliseconds on 8K processors. And here's the third picture, just to, okay, so the picture corresponding to that is here. You can see that the blue and the green, the PME and the non-bonded, are very nicely overlapped. This is one of those features of CHAMP++ that we tout often, that you can independently develop modules and interleave their execution on processors, and thereby kind of use idle time in one module for useful computation in the other. You can see the benefits of that right here in this picture. It looks like it's scaling pretty well. As you can see in the previous picture, the red curve is going down, but if you look at this, you can see the structural limitation. The critical path is almost reached. There is very little slack there. Just to complete the thing, here is a 100 million atom simulation running on 300,000 watt, 298,000 some cores of Titan, and you can see that this is actually slightly different picture. 3 steps without PME, 4th step with PME, and you can see that the particle mesh AWOL, the FFT, forward and backward path, start to dominate the execution here. So this is the challenge that we're working on now, but even here, average time step is 13 milliseconds, which is pretty good for now. So this is the 100 million going up to 298K processors, and you can see the performance improved in the last year from 26 milliseconds to 13 milliseconds at the bottom there. You'll hear a talk about energy. Supercomputing 11, we had a paper by Osman about saving cooling energy. The idea simply is to increase the thermostat in the machine room. And if you increase the thermostat in the machine room, what happens? The cores can get hotter. If the cores can get hotter, we can actually sense the core temperatures every few seconds in the runtime system, and then decrease the frequency of the chips that get hot. Well, if you do that, you all know what happens. Load imbalance, right? Some chips are running slower, there is dependencies, and so that means everyone is going to run slower. And so this problem we can fix with the adaptive runtime system. We can migrate objects around away from the heated processors, and so with this we can actually save cooling energy while reducing the timing penalty that you get for it. So this was actually a very good result, and we are continuing on this work on energy awareness with energy signatures of different functions or entry methods inside the application, and then differentially changing frequency within each iteration and combining that with somehow the temperature monitoring as well. That's one of the ideas that we're working on. There is of course overhead associated with changing frequencies, and we have to trade that off carefully. We are starting to work on network energy a little bit, maybe not worth spending time on it. So next couple of topics: fault tolerance. There will be a talk on the power aware computing by Usman. For fault tolerance, CHAMP++ now for maybe last 4 years or so, probably more, I don't know, has supported in the production version the in-memory checkpointing scheme. So you can take any CHAMP++ program, especially if you are running on workstation cluster, just go and kill -9 one of the processes and it will continue to work. And so that's the in-memory checkpoint. We also have an experimental version on message logging that is advancing in many ways. In-memory check or in local storage is probably the right way of saying it, with all kinds of local storage now becoming feasible. And it's practical for many applications because especially the ones that have small memory footprint, you can actually accommodate them in memory. And so we have some recent results. We developed a new fault injection method that allowed us to show highly scalable results, and it turns out that the times are truly remarkable and dramatic, and I will let Gangbin talk about that later in his talk. On message logging, there is no talk today, but we have quite a few results this year. The idea of message logging is that if a processor fails, if a node fails, we don't want to send all the nodes back to their checkpoint. Only the failed one needs to retrieve its state and bring its execution forward. To do that, everyone needs to store the messages and resend them to the failed processor. This method by itself has very few advantages compared to checkpoint restart, except maybe some energy savings. But in fact, combining with over decomposition, it turns out it has a much more significant benefit because you can parallelize the restart. And I won't belabor the point of that, except that a failed node contains many objects. Those objects can go to separate processors and recover there. So you can parallelize the recovery, and this turns out to be, quite MTBF can be shorter than checkpoint period, for example, and you still make progress. So last year, this project made significant progress. Things like simple causal protocol, team-based load balancing, and so on, and multi-core optimizations. These are appearing or have appeared in multiple workshops. The other highlight, again, there will be a talk tomorrow morning about this, is the HPC challenge competition, which was conducted at supercomputing. And the class 1 is for machines, class 2 is for programming models, and we implemented LU decomposition and 3 of the lead MD, which is mini MD, pretty much exactly as a mini app, and then couple of required ones, Bansat and random access. And in all of those, LU decomposition, for example, is only 1650 lines of code, and it achieves 67% of peak on Jaguar. So among all these competitors, CHAMP++ won the award for class 2 productivity. Within that, they split it in two, and CHAMP++ and Chapel shared the class 2 award this year. So that was a good morale boost and a recognition. I think I'll skip the results for those. Phil will hopefully talk about that tomorrow. One of the other things I did many years ago, maybe Rob will remember this, used to talk about this, maybe right after actually you left. The interoperability was a big thing when we developed Converse, which is the underlying layer in CHAMP++. the idea of the name converse comes from the ability to talk, converse among different programming paradigms, but it was kind of gathering dust, and we had to redo and do some new implementation to make sure that MPI applications, not adaptive MPI, which is our own implementation of MPI on top of Charm++, but plain MPI, the native MPI provided by the vendor, applications written using MPI can use modules written in Charm++ and vice versa. So that was the objective of this project, and in fact we can call Charm++ libraries from MPI program now. I'm hoping this will give a boost to the adoption of Charm++ by various, at least people can test the system and see if they test the waters, as it were, in a small one module kind of way. So you can do time sharing where MPI runs for a while, then gives control over to Charm++, which can do its message-driven execution, then come back to MPI again. You can do space sharing, a subset of processes running Charm++, or you can do space and time sharing combined. Of this, time sharing is very stable right now. Space time sharing together is being tested. So I guess you all know this. Most of you, it's a very robust system. We have a very strong nightly build system, 50,000 plus users, although most of them are probably NAMD, but there is a significant number of others as well. It runs on many combinations of machines, compilers, and OSs. So those of you who haven't tried it outside the group, please, this is a good time to take a test drive. The last part is raising the level of abstraction. There is a language level work that we have been doing. Let me just talk about the Charisma, multi-phase shared arrays, and divide conquer. This is the last one, is a new, a relatively new one. I called it DivCon here, but Pritish has a different name for it, and there'll be a talk on this. It's a functional like language. It combines task parallelism and allows you to deal with distributed data arrays as well. There is also work on parallel state space search that we did way back when, but now we have started a new one, which is called Parallel PRASSE framework that Yanua and Pritish worked on. So all of that actually now we're working on. So we're building a charge, which is a compiler infrastructure and a new language. So that so far what we have done is library based. We're working on a new thing that is a compiler based, convenient syntax, natural optimizations, and Aaron will be telling you about that later as well. There's a lot of talk about evolution versus revolution these days within the DOE circles, and I thought of, if I think about evolution in the biological sense, right, what happens when there is a revolution in biological ecosystems? An asteroid comes and hits, what happens? There is a shock to an evolving system, right? And when there is a shock to an evolving system, maybe such as the exascale, what happens? Well, okay, some things become extinct, some things become infeasible, and the rest have to quickly evolve. That quick evolution in the programming model sense is enabled by interoperability. You need to have multiple execution, multiple languages interoperate with each other, and at the end of that, what happens? You don't get a single winner, although there is some winner, but someone that dominates the ecosystem, but you get an ecosystem of a multiple species. So I think we'll get a collection of viable programming models that interoperate as we go further into the next 5-10 years of exascale era. So the last but not the least point, at least from the way what weighs on my mind these days, well, we are working on a book that should be coming up this fall or a little bit later on the science and engineering applications that we have been developing over the years, and this will have chapters on various applications that we have developed in science and engineering over the years, and maybe a few introductory chapters on Charm++. So expect that in the next few years, and I think I'll stop with that. Okay, thank you.